We're going to have a look at this idea of multiple roots. So this is, I guess, the extension part, or the extension 2 part of polynomials. If a polynomial it's a multiple root, so a double root, triple root, whatever, it's multiplicity, we'll just call it n, whatever it happens to be. Then the derivative will also have a root, but its multiplicity will be one less. So what we're saying is, if its multiplicity is higher than 1, when we differentiate it, we're still going to get something that its derivative is going to be 0. We can prove it more formally and say, all right, well, the polynomial, therefore, will factorise to be x minus a to some power times some other polynomial. That other polynomial, by the way, we know that m has to be bigger than 1 because we said it was a multiple root. And x equals a can't be a solution of qx, because otherwise that would increase the order of the root a. We're saying it's of order m. So let's differentiate it. We'd have to use a product rule. So write down the first, diff the second. So differentiate qx, q dash x. Write down the second, diff the first. We're going to use our chain rule or anarchy. Bring down the power, lower the power, diff the inside. That has a common factor of x minus a to the power of m minus 1. And inside we get x minus a, q dash x, mqx. So it is equal to x minus a to the power of m minus 1 times some other polynomial. So therefore, what we're saying is the derivative, it does have the same root, but of order 1 less. And so by our factor theorem then, we can find out where multiple roots are, because if we know it's also a root of the derivative, we can solve the derivative equals 0, and that will tell us, we must have a double root. And second derivative equals 0, must be a triple root, and so on and so on. So, and we know a is not a root of this rx because we said it was not a factor of qx, so therefore it would be impossible to factorise rx and get another factor of x minus a. Okay, well, so there's a more formal proof of the idea. So now we're going to solve this equation, but they've told us it has a double root. So what I'm going to do, rather than just guess which one it's going to be, I'm going to find its derivative, because if it's a solution to this, it must also be a solution to the double root, or the derivative. And the derivative will be a quadratic, and quadratic's a lot easier to solve than a cubic. So let's differentiate it. 3x squared minus 8x minus 3. We'll find when that is equal to 0, it factorises quite nicely. We get two possibilities for the double root. But if we have a look at the original polynomial, one of those would be logical and one would not be. Which is the logical one? Why? Yeah. Okay, so x minus 3. 3 is a factor of 18. And also we've got monic, so x is nicer than the 3x. So if I was going to guess which one, I'm going to go for the 3. I'll test that first. So it's either minus a third or 3. I'll test that one. That's not going to be possible because we know 3x plus 1 is not a factor. I just did it by inspection. If I sub it into the polynomial, yes, indeed, it does work out to be 0. So I know that that is the double root. So when I factorise it, I'll get x minus 3 squared, because I now know it's the double root. And then I can work it out constant times constant and so on. The other factor must be x plus 2. So minus 2 or 3. Remember, it's not sufficient just that the first derivative is equal to 0, because I had two answers for that. Both of them must be equal to 0. The polynomial and the derivative must be equal to 0. Oh, I like this one because it was in the year 1991, which is very symmetric. But look at the question. It's very symmetric too. X to the power of 4, ax cubed, plus bx squared, plus ax plus 1. So it was a nice year to put that symmetric type question in. I'm sure you thought exactly the same when you saw it. And in case you're wondering, 2 plus b squared can't equal 4a squared. You probably noticed that as well. We'll see why later on. There is a reason why that is actually turns out to be important information. All right, they're telling us alpha is a root. We need to show that it can't be 0, it can't be 1, and it can't be negative 1. Now 0, I guess, is obvious because we know that you must multiply together to give 1. So 0 is not going to be 1. But 1 or negative 1, were actually logical ones to test. And we're saying, well, it can't be a root of this. Well, how do we show that? Let's do the easy one first. Well, polynomial 0 equals 1, so it fails the factor theorem, so alpha can't equal 0. But what about 1? If I sub 1 in, I get 2a plus b plus 2. Well, I can't actually say that that can't equal 0. So let's have a look at minus 1. I get a very similar expression, minus 2a plus b plus 2. I need to be able to show that these aren't factors. This is where it comes in useful. They told me that 2 plus b squared can't equal 4a squared. Well, if that's true, 2 plus b can't equal plus or minus 2a. And rearranging that, I get plus or minus 2a plus b plus 2 can't equal 0. So therefore, polynomial 1 can't equal 0, polynomial negative 1 can't equal 0. So 1 or negative 1, they're not solutions either. So no good. That tells me something about this little polynomial. What does it tell me? Yeah, there's going to be no real roots to this. Because the logical ones were 1 and 1, and it's monic. And we're talking about a polynomial here, not an equation. So there must be no real solutions. We must have 4 imaginary ones. Show that 1 on alpha is also a root. So we know alpha is a root. We don't know what alpha is, but we're going to show its reciprocal is also a root. Well, polynomial 1 on alpha would be this lovely expression here. If I'm going to show it's equal to a root, I've got to show it's equal to 0. Let's make it all one fraction. Common denominator would be alpha to the power of 4, and that symmetry turns the top into something quite nice. It is the original polynomial, you'll notice. And we know polynomial alpha is equal to 0. So that is what I've in fact got on the top. I've got polynomial alpha. So it equals 0. So yes, it will be a root. So if alpha is a root, 1 on alpha is also a root. We still don't know what they are. We show one's alpha, one's 1 on alpha. So we're going to now deduce that if alpha turns out to be a multiple root, its multiplicity must be 2. It must be a double root. And further, we're also going to deduce that 4b is equal to 8 plus a squared, because that just looks like fun. All right, follow my logic. All right, say we're listing our roots. And we now know, what we've proven so far, is that if alpha is a root, 1 on alpha is a root. So if we create our list, every time we write down alpha, I'll write down 1 on alpha, because I know that's also a root. But we're saying if alpha is a double root, so I'm going to write down alpha twice. It's going to appear in my list twice. But every time I write down alpha, I'm going to write down 1 on alpha. So if alpha is a double root, 1 on alpha must also be a double root. Okay. So I now have 4 roots. But it's a quartic. So there are no more roots. So what we're saying that if alpha is a multiple root, then it could only be of multiplicity 2. So if alpha is a double root, then that's it. You can't have any more alphas in there, because the other 2 will be the 1 on alphas. So it's a quartic, got a maximum of 4 roots. So no roots, therefore, could have multiplicity greater than 2. Now, the next bit, proving that 4b is 8 plus a squared. Well, differentiate it, because we now know it's a double root. I'm going to play with the roots of this equation. We know one of the roots of this equation will be alpha, because if alpha is a double root, it will be a root of the derivative. But we said 1 on alpha is also a double root. So 1 on alpha will also be a root of the derivative. There'll be a third one because it's a cubic. Don't know what it is, call it beta. I know they'll add together to give minus b on a, so minus 3/4 a. Some of the roots. Some of the roots 2 at a time. I might not need all these things, but we'll see how we go. By the way, that's how you write some of the roots 2 at a time. Sigma, alpha, beta. Good. Some of the roots 3 at a time is good, because the alpha and the 1 on alpha cancel. And so we can actually work out the other root is, in fact, minus 1/4 a. what I've now got is a couple of equations I can play around with, simultaneous equations. I'm going to substitute 3 into 1, and I made alpha plus 1 on alpha the subject of this one. So now alpha plus 1 on alpha is minus a half a. If I substitute 3 into 2, voila. If I substitute 3 into 2, you'll see the expression I get up the top here. But I've factorised the a, and that's going to be alpha plus 1 on alpha, which I've just said is a half a, and then it just follows through algebra, the final part there. That's one way of doing it. There would be other ways of approaching that problem. Okay. So in our pretend Cambridge, 5B, but also in Patel, there's a handful of questions we'll look at as well.